Good afternoon everyone. So this is my next lecture in continuation with the lecture number 12. So this lecture is similar to the earlier lecture, that is based on PN junction. Here we will see about PN junction, space charge width, and then we will see about Zener diodes. So as we have already discussed about built-in potential, PN junction biasing and other things, other parameters. So we will discuss here what is depletion width or space charge width in the PN junction. So we have already seen that built-in potential which is given by VBI is equivalent to KT by E ln ND NA upon NI square. So this formula is for having the value of the built-in potential, so that there will be a crossing of electron from N junction to B junction will be easier. So we have already seen that the value of the germanium is 0.3 volts and for silicon it is 0.7 volts. So here we have the depletion width region, because when we do biasing, that is the forward biasing or a reverse biasing, there will be a change in the depletion width. So as in the case of the forward biasing, there will be the reduction in the depletion width, and in the case of the reverse biasing, there will be the increment in the depletion width. So this is the equation which belongs to VBI, which is built-in potential also. So equation for width of depletion layer in open circuit when there is no voltage applied, which is given by W is equivalent to under root 2 epsilon by Q 1 upon NA plus 1 upon ND multiplied by VBI. So on putting the value of VBI, that is KT by E ln ND NA upon NI square. So for example, if you have ND 10 to the power 17 per centimeter cube, NA 10 to the power 15 per centimeter cube, and for silicon we know the value of Ni, which is equivalent to 1.5 into 10 to the power 10. So by putting these value, you can calculate the VBI for silicon, which is around 0.635. On putting the value of KT by E is 0.0259. So you just put this value, built-in potential here, the value of Na and Nd, which is the acceptor concentration and the donor concentration, then 2 epsilon, where epsilon is basically epsilon naught, epsilon r. So epsilon r, value of epsilon r for silicon is, which is mentioned here, that is 11.7, and for germanium it is 16. So if you want to find out the value for silicon, the depletion width, you have to put the value of epsilon r is 11.7, epsilon naught is 8.85 into 10 to the power minus 12 farad per meter, or in farad per centimeter you can have this value, that is 8.85 into 10 to the power minus 14. So in numerical problems you have to put this value in centimeter, because we take the value of VBI, built-in potential, NAND is basically in per centimeter cube. So just put down all these values and you can easily calculate the value of the width of the space charge. So basically this space charge width is a combination of P and N junction. So it is equivalent to W is equivalent to Xn plus Xp. We have N region width and we have P region, some P region width, which will give you the value of the W. So here epsilon is permittivity, epsilon is, as I have discussed, epsilon naught multiplied by epsilon r. Epsilon naught is absolute permittivity of free space, which is equivalent to 8.85 into 10 to the power minus 12. In farad per meter or farad per centimeter, it is 10 to the power minus 14. And the values of epsilon r is 11.7 and for silicon, and for germanium it is 16. So on putting the values, you can easily find out the built-in potential and the space charge width. So next we have diode equivalent circuit, which is also called a small signal model of the diode. So we can represent here the diodes in different models. Like the first one is the piecewise linear model, the second one is the simplified model, and the third one is the ideal device. So we can see from the points which I have mentioned here, the small signal model represents the internal voltages, resistances, capacitances across the diode. So the equivalent circuit of the diode turns on voltage, which is basically knee voltage or built-in voltage, and internal resistances, that is R. So in the simplified model, we represent only knee voltage. So first, the second model, which is basically simplified model, we have the knee voltage, the ideal diode, and we represent here a knee voltage only. Okay, so right, so in the case of the piecewise linear model, we have a voltage which is knee voltage, a resistance source also here, then there is an ideal diode. So due to resistance there will be the restriction in the current, and that's why the current will flow whenever we increase the voltage in the forward biasing. In the ideal condition, we have only diode, it doesn't have any knee voltage, any resistance there. So the current, whenever you put a voltage just 0.1 voltage or point something exceeding the 0 voltage, it shows a sharp change in the current. So in the simplified model, we represent only knee voltage, which is a very important point, and the ideal diode represents the ideal characteristic basically, which is basically ideal characteristic is what? The current will increase automatically when you apply a voltage. It doesn't require the voltage to cross the knee voltage point. So next we have diode equivalent circuit in reverse bias mode, which represent the junction capacitance with some internal resistances. So there are three circuits which I have shown in the right side. That is equivalent circuit for a reverse biased diode. Then the second one is the equivalent circuit for the forward biased diode. Then the last one is the AC equivalent circuit for a forward biased diode. So we can see here that the diode equivalent circuit in forward biased mode represent the diffusion capacitance basically with internal resistances and knee voltages, which is in the middle one. The AC diode equivalent circuit represents the capacitance and the internal resistance of the diode. So it represents the internal resistance. This is your internal resistance, and this is basically capacitance. So in the AC equivalent circuit, we have internal resistances and capacitance. Next, we have a small signal model of the diode. How in the forward bias, how we represent a circuit. So here we are taking one capacitance in parallel with one resistance, and there is a voltage source, and their current will flow across this circuit. So I is basically given by, obviously at this point there is the same voltage which is applying on the input side. So I is equivalent to V by R for this loop. Then across the capacitance we have C multiplied by dVA upon dt, because the voltage is here is V again, but it is equivalent to C dV by dt. So the total equation for the current will become I is equivalent to VA by R plus C dVA upon dt. We can take the values of di by dt with the help of the resistance. So 1 by R is equivalent to di upon dV, that is d upon dV multiplied by, because I dc we have calculated from here, we just put the value in the equation, or we can put the diode value, the diode equation, current equation. So that is equivalent to IDC is equivalent to I naught e to the power QVA upon KT minus 1. And when you solve this equation, you will get this term, that is d upon dVA I naught e QV A upon KT. So for the small signal conductance, we have G is equivalent to 1 upon R, and that's why when you calculate 1 upon R value, which is equivalent to d upon dVA I naught e to the power QVA upon KT, and just put these values, you will get the value of G as IDC upon KT by Q. So this is the transconductance or the conductance of the small signal model of the diode. So how the charge storage is will occur in the PN junction diode. So there are majority charge carriers and there are also minority carriers in the PN junction. So we have excess minority carriers in the quasi-neutral region. So as I have discussed you that there are two regions basically. The first, this is, suppose this is P and this is N. So first region belongs to P region, which is your XP, and this region belongs to N region, which is your XN. So from minus XP to XN we have the our PN junction. So you can see from the diagram, from minus XP to XN, at minus XP we have the number of, or the concentration, excess carrier concentration represented by del N Px, and for the N region we have the excess minority carrier concentration, because in the P region we have electrons in the minority, in the N region we have holes in the minority. So in the P region we have delta N Px, and in the N region we have delta Pnx. So majority carriers is stored at the edges of the depletion region, and in the depletion region we have minority carriers. So in the depletion region we have minority carriers, and this rho x will give you an idea about the density of these charge carriers. In the p region there is minority carriers electrons, and in the n region there are minority carriers holes. So next we have p-n junction small signal capacitances. So these are some formulas for calculating the capacitance of the p-n junction. Normally C is equivalent to Q upon V, and with this formula we can get our formulas for the depletion capacitance and diffusion capacitance. So there are two types of capacitances associated with a p-n junction. The first one is the depletion capacitance. So in the depletion capacitance is basically due to the variation of the depletion charge. So whenever there will be a variation in the depletion charge in the depletion region, there will be occurrence of the depletion capacitance, and in the same way there is diffusion capacitance, which is due to variation of the stored minority charge in the quasi-neutral region. So for a one-sided p-n junction, Q is equivalent to Qp plus Qn, which is total combination of the charge in the p-n and the n region, and that charge is given by that capacitance is given by diffusion capacitance, which is dQp upon dVA, or it is given by tau p di upon dVA, which is equivalent to tau p into G, that is tau p into IDC upon KT by Q, which we have called as conductance. So G we have already calculated, which is IDC upon KT upon Q, and with the help of G we can easily calculate by multiplying with tau p, that is the time the holes will reside in the P region. We can calculate the junction capacitance for the diffusion site. So next we have variation of the diode capacitance. So variation of capacitance across the diode with respect to the voltage represents the forward biased and the reverse biased capacitances as shown in the figure. So we have capacitances in picofarad, and in the x-axis we have voltage. So in the forward bias we have a higher capacitance value, in the reverse bias we have lower capacitance value. So the conclusion is that the capacitances increase with the applied voltage. As you increase the applied voltage, so in the forward biasing the capacitance is more as compared to the reverse bias. So we have capacitance forward biased is increased and capacitance in reverse bias it decreased. So as you increase the voltage, C or capacitance value will keeps on increasing. So next, the second part of this PPT belongs to ZENER diode. So the next we have, what is ZENER diode? Normally there is a p-n junction diode. p-n junction diode and ZENER diode, there is almost same characteristics, but we have the symbol is different for ZENER diode. There is a ZENER breakdown also mechanism which occurs in the case of the ZENER diode. So analyzing a diode operating in the reverse bias region, normally ZENER diode will work in the reverse bias region, will show that the current through it remains essentially constant until the breakdown voltage, also it is called as avalanche or ZENER breakdown voltage, is reached. At this point the current will increase very rapidly for a small voltage change. So if I consider the difference between the p-n junction and the ZENER diode, in the ZENER diode the reverse bias current is more as compared to the p-n junction diode. So the characteristic is almost same, where if you see the VI characteristic, when you increase the diode voltage there will be a change in the current in the forward bias. Similarly, when you increase the diode voltage in the reverse bias case, so there will be a change in the current, but the current will drastically increase in the reverse bias after a breakdown point. So this particular point which is represented here, this is your ZENER breakdown voltage. ZENER breakdown voltage, and this particular I0 will give you an idea about how much is the current will flow, the minority current will flow when we do the reverse biasing in the case of the ZENER diode. The symbol for the ZENER diode is same, it's a simple symbol like a p-n junction diode. In the p-n junction diode we have this type of symbol, but in the ZENER diode we have Z shape in the upper part of the diode. So this looks like this, and we have the reverse biased and neglected in the Zener circuits normally. So we have the PN junction diode, a resistance value, and in ideal diodes we have there is no Zener breakdown mechanism in the PN junction diode. But on the other hand, if we consider about the Zener diodes, there is a breakdown mechanism which is avalanche or Zener breakdown voltage, which occurs in the Zener diodes. So what is Zener diode symbol? We have discussed that this is the positive part of the Zener diode and this is the negative part of this Zener diode. This is a Z shape symbol, and the positive is the same as the PN junction diode. This is the anode and this is the cathode. The diode is in the reverse bias condition. At some point the reverse bias voltage is so large that the diode basically breaks and the reverse current increases dramatically. So this maximum voltage at which the diode breaks, or there will be a sharp increase in the current, is known as avalanche breakdown voltage, and the current is also known as avalanche current. So this is an important part, which is avalanche. Sometimes it will be asked what is avalanche breakdown voltage and what is avalanche current. So you can give an example of the Zener diode and the difference between both the Zener and the PN junction diode. So we have this type of characteristic for the Zener diode, as in the earlier slide I have already shown you. The blue line shows whenever you increase the current in the forward bias, there will be a change in the current in the reverse bias, forward bias conditions. So when you increase the voltage, there will be a change in the exponentially increasing current. So this is exponentially increasing current, and in the reverse bias condition there will be a Zener breakdown. So at this region, at this point there is a Zener breakdown, and this voltage, this Vz, is called as Zener breakdown voltage. This is so next we have the resistance level. So semiconductors acts differently to DC and AC currents, and there are three types of resistances. The first one is the DC or static resistance, the second one is the AC or dynamic resistance, and the third one is the average AC resistance. So we just look up upon these type of resistances, how they can be implemented in a particular, with the help of the particular diodes. So the resistance of a diode at a particular operating point is called as the DC or the static resistance diode, and it can be determined using this equation. Normally V is equivalent to IR or R is equivalent to V by I. So this is the simple resistance value, which is the static or DC resistance. So this is DC or static resistance, which is VD by ID, or the slope. You can find out the slope of the particular resistance. Next we have the AC or dynamic resistance. So static resistance is using DC input. If the input is sinusoidal, the scenario will be changed. So in the static resistance case, we have only DC input, but when we apply AC input, the scenario will change. The varying input will move instantaneous operating point up and down of a region, and thus there will be a specific changes in the current and the voltage obtained. So there will be some difference in the current and the voltage obtained, and that difference we have to calculate with the help of the graph. So RD is equivalent to delta VD upon delta ID. This is for your AC or dynamic resistance. So next we can see from the plot that how average AC resistance will give you an feel of the characteristic between V and I. So delta VD, that is from the in the x-axis, that is 0 to 0.1 to 0.2, 0.1 scale difference, and delta ID, which is 5 scale difference in milliampere. So this is 5, this is 10, then 15, then 20. So average AC resistance we have RAV, which is equivalent to VD upon ID, point to point. So if we calculate here from point to point, this point to this point, we have the difference in the voltage is given by this basically. So this is delta VD or delta VD, and this difference, which is shown here. This is your delta ID. So we have a difference of, from here you can see that 15 to 18 or 18 to 3. So there is a difference of 15 milliampere. So this is a difference of 15 milliampere. And here there is a difference of 0.2 point something, like delta ID is equivalent to 15 milliampere and delta VD is equal to around 0.1 volts. So we can calculate our average, which is equivalent to delta VD upon, this is delta VD upon delta ID. So delta VD is equivalent to 0.1 upon 15 into 10 to the power minus 3. So we can calculate 0.1 into 10 to the power 3 upon 15. So by this way we have around 100 upon 15, or it comes out to be 6 point something, 6.3 something. So this is the value of the resistance in a dynamic manner, or in a it is called as AC resistance. So this is your AC resistance. So till now what we have discussed about the PN junction, we have discussed about how the built-in potential will be used in the calculation part of the PN junction, how we can fix a particular voltage so that there will be an increase in the, whenever we increase the voltage beyond that built-in potential, only in that case the electrons will move from N junction to P junction or from P junction to N junction. Then we have discussed about space charge width, the depletion width, whenever we provide the biasing. In the case of the no biasing condition, or in the case of the forward biasing condition, whenever we provide biasing, there will be a change in the depletion width. When there will be a no biasing condition, there will be a no change in the depletion width. When we provide a forward biasing, the depletion width will get reduced. When we provide reverse biasing, the depletion width will get enhanced. So we see, according to the application, we see what is the requirement for the biasing. So how the applications can be performed using biasing, like wherever we need forward biasing, we apply forward biasing in the case of the lasers, in the case of the LED. But whenever we require reverse biasing, as in the case of the detectors we have discussed earlier, so there is a requirement of reverse biasing. So whenever the light will fall on the detector, then only there will be generation of the current, or the electron hole pair generation is there. So next, in the next lectures we will see how the PN junction will perform in the small signal models. We have already discussed about how small signal models will work. We see some numericals based on Fermi levels, how the Fermi levels has to be fixed for the conduction and for the valence band, how we can calculate the intrinsic and extrinsic concentration of a particular semiconductor. With the help of these some equations, like intrinsic equation, like we can see that in the case of the intrinsic equation we already discussed earlier, Ni, which we can calculate with the help of NC/NV exponential minus Eg upon kT. But there will be some parameters by which we can fix the value of Nc and Nv, because Nc and Nv is directly proportional to temperature to the power 3/2. So with these formulas we can calculate the value of the intrinsic carrier concentrations and all. So in the next lecture we are going to see how these intrinsic carrier concentration plays an important role in a semiconductor material, how we can fix the value of the, calculate the value of the intrinsic carrier concentration. Similarly, on the other hand, we see the ZENER breakdown. Similarly, we have avalanche mechanism, how the performance of the PN junction will be based on these ZENER and the avalanche mechanism. We see whether the intrinsic carrier concentration will perform the better things and all other things in the PN junction diodes. So meanwhile we stop here and we will see the PN junction diode characteristics, as we have already discussed in the forward and the reverse biasing conditions, how these forward and reverse biasing conditions will be performed and how these can be applied in a numerical problem. So we have not covered any numerical till now in these topics, like in the PN junction and all. So built-in, how to calculate a built-in potential, how to calculate the value of the Xn and Xp for a particular space charge width, the depletion region. So for that depletion region we have to calculate the value of the PN junction xn and the xp value, and then with the summation of these xn and xp value, we can easily calculate the value of the total width of the depletion region, which plays an important role. So these numerical problems we will cover in the next lecture. Along with that, we cover some concepts of the MOSFETs and all. So MOSFETs, the depletion type MOSFET and the enhancement type MOSFETs, and these topics will be covered in the later on lectures, along with these numericals based on the PN junctions. Thank you so much.